Hello everyone, today I'm going to be talking about the differences between static meshes, instanced static meshes, and hierarchal instanced static meshes. You could use this knowledge if you have many similar meshes in your scene and you want to improve performance. I will cover topics for lowering frame times and having faster level load times. I'm covering this topic because I released an update to my Spline mesh tool on Fab. It's free to download the blueprint itself and includes a demo map if you purchase either tier on Fab. But I mainly use Fab as an optional system to help fund future updates and Discord support for this. Every day after its release, I'm posting a new video about something coming to the tool, and today it's about using the different static mesh types that will be able to be put along the spline. All my demonstrations for this video will involve the spline tool, but this information can be used outside of the tool if you're using these mesh types. So let me start by defining each type. A static mesh is any type of 3D model that gets imported into UE5. The geometry can be moved around, rotated, and scaled, but the overall geometry remains the same, hence why it's called a static mesh. A static mesh exists as either a component or an actor. The component means it's attached to something bigger, like a blueprint, and cannot be placed in the level by itself. A static mesh actor can exist in the level by itself, and whenever you pull a static mesh out from the content browser and put it into your level, it becomes a static mesh actor. They both have the same type of options, but they are implemented differently. For the majority of this video, we will be talking about static mesh components when I say static mesh, because the way I'm using it is a part of this blueprint. Going back to the three types of meshes, static meshes are the easiest to set up and use out of the three types, but also runs the slowest. Then we have instanced static meshes and hierarchal instanced static meshes, which I will be referring to as ISMs and HISMs from now on, because saying hierarchal instanced static meshes is quite a mouthful. ISMs and HISMs are both ways of grouping a bunch of the same static meshes together and sharing the computation for rendering. This is really helpful when you have a lot of the same meshes in your scene. To demonstrate this in an abstract way, consider the following addition problem. It may take you a while, not because it's difficult, it's just a lot of math, and I see that the numbers appear in multiple places. What if I just knew how many 1s, 2s, and 3s are being added? Well, suddenly this is a lot easier to calculate. By using multiplication instead of a bunch of tedious adding, we can calculate this a lot quicker. We batch the calculation for these numbers to get a quicker result, similar to how instancing batches meshes together to calculate it as a group instead of each mesh individually. Now, if we only had one of each mesh, the multiplication here doesn't really help us. In fact, it actually makes it more complicated. This shows how it could be beneficial to combine a lot of the same meshes into instances, and that it would become less helpful when having fewer instances. You may be thinking there's some magical number where if you have 2, 5, or even 50 copies of a mesh, that suddenly you should switch over to using instances. The magic number is 2, but with multiple caveats. Some caveats being loss of functionality per mesh and the added complexity of setting it up. Now, the complexity is already handled with this tool, but if you're using something else or creating your own, it probably isn't worth it for 2 instances. The functionality loss caveat can be simplified into saying anything that used to be able to do to a certain static mesh actor is now spread to all instances. For animation, they all move together. For collision, they either all have it or none of them have it. For materials, they all share the same material. The only limitation I know of to this rule is that you can't have physics operations affect instances, even as a group. But for nearly everything else, whatever happens to one instance happens to all instances. Now, what about performance? Well, first we need to know how we're measuring performance. A lot of people will say it's the frames per second, but that's actually not the main thing that instancing helps with. In Unreal Engine, you're only as fast as your slowest component, either in the CPU or GPU. Most people using Unreal Engine will be bound by their GPU time. Instancing helps with CPU time. So as long as your GPU time is slower than your CPU time, you won't notice that many additional frames per second from instancing. It will save a little bit of GPU time by using less memory, but even if your CPU time is fast, there's one crucial performance metric that it helps with, and let me show it through a demonstration. I have this blank scene with just one blueprint and one light source for testing. If we type stat unit in the command line, we can see the number of prims, draws, and performance timing for these meshes. A lot of the main components that instancing affects. Let's start with prims, which are also called primitives. Primitives are one of the markers to tell how much information the editor is running through. It's not the most accurate number because the editor itself affects the number, but if nothing else besides the meshes in the scene are being altered, then it gives a decent comparison. Watch as I click on the background on this empty scene. The prims go up purely because it's adding text in the output log. Once the log fills up, the prims stop going up because it's still showing the same number of messages. There's no recommended number of primitives, but if you start going into the billions, you should have a justified reason. Another performance marker is the draws, or more commonly known as the draw calls, and this is a really good indicator of how much your meshes are stressing your scene, since the meshes are the main thing that influence this number. Draw calls measure the number of instructions that the CPU has to send to the GPU to calculate the look of the mesh based on the material, mesh geometry, and other factors. This does mean that some project settings can multiply the draw calls or add complexity to each call, like post-processing, lighting, transparency, and multiple materials on one mesh. If 10 static meshes share one material, it runs 10 draw calls because each mesh is treated as an individual. But if 10 instances share one material, it is one draw call. Increased draw calls typically slow down your CPU when these meshes are initially called. Now to look at raw timings. I mentioned before that we won't see a lot of increase in our frames per second, and you can see that reflected here. What it does save you is that one-off loading time of loading these meshes in your scene. That initial loading difference can be quite massive, and if you have a lot of instance meshes, it could speed up loading times between levels significantly. I can test this in the editor by just having a lot of high poly walls placed side by side to purposely tank performance, and then have it load in as both normal static mesh components and ISMs. I added a timer function that just tells me the timing of each blueprint update. I'll leave these functions in the official blueprint, and they can be enabled by using this advanced variable. But from this, we can click on Use ISM and see the timing here, and then uncheck it and see the other loading time here. It's a nearly 2.5 times difference in loading times. Now just remember, this is only for editor timings. You would want to use trace logs and package builds to see the exact timings that players would feel. Even if this only adds 1/10 of a second to loading times, you have to remember that this is just one thing being loaded. And if you add 100 similarly sized assets, it could be a whole 10 seconds before actually playing, which can be frustrating for players. There's one more thing to look at though, and that is the actual memory being used that is causing loading times to be faster or slower. To see the memory used, we will need to call stat scene memory in the command line. For non-instance components, we can see nearly 19 megabytes are being used in this blueprint, but when instancing, the primitive memory drops to less than 1/10 of a megabyte. This is what 5,000 unnecessary identical meshes can add to memory. This additional memory will increase loading times. So now we know what we're looking for when we say better performance. We aren't looking for more frames per second because typically that is more likely to be bottlenecked by the GPU. It's important to remember that it's still rendering the same amount of geometry whether it's through instancing or not. The more geometry there is, the worse this frame time will be. And to be clear, these meshes have atrocious geometry and then are being multiplied by 5,000, which is why my frame time looks bad for seemingly not a lot happening in the scene. And while instancing can help CPU times in the scene, it's much more likely to be overshadowed by the GPU usage, which is why instancing is better measured in load times. So now we know why ISMs and HISMs can be better than static meshes, but what's the difference between ISMs and HISMs? The main difference is that HISMs have different levels of detail, also called LODs. As I'm sure many of you already know, LODs are multiple versions of the same mesh that go from high quality to exceedingly lower qualities, and the lower quality versions of the mesh help improve processing time. The LOD on an ISM is shared between all instances, so they are either all high quality meshes or all lower quality. But in reality, we want the meshes close to the player to be high quality LODs and the ones further away displaying lower quality LODs, since the player can't tell the missing detail due to how far away the mesh is. This is the special purpose of HISMs. They allow each instance to have different LODs that the developer provides. So that's the main difference between ISMs and HISMs. As a quick note to UE4 users, in Unreal Engine 4, ISMs were worse than HISMs in that if one instance was in view, all instances were calculated, which is why HISMs were used more in UE4, but that was fixed in UE5, so now I recommend developers to only use HISMs if you have specified LODs and have a reason for using them over Nanite. And if you are using UE5.4 or above, ISMs are actually more reliable than HISMs and inherited the functionality of using LODs per instance. My general recommendation is to use ISMs in UE5, but in versions 5.4 and above, there really seems like there's no reason to use HISMs. The only exceptions are if you have thousands of static instances that are spread far apart, which is mainly foliage actors that don't move other than material animations, or the other exception being that you're developing for lower-end hardware. Some of you may have noticed that the LOD system in HISM sound a lot like Nanite, because Nanite is a type of LOD system, but Nanite makes the LODs of the meshes automatically, whereas you have to provide each LOD in the HISM and set the transition periods where each version needs to load in. Nanite also makes the LOD with the player's sight in mind, so that places on the mesh where players would notice a lot of detail missing would be higher quality and unseen parts of the mesh would be lower quality. HISM LODs do not do that. They don't change geometry and do not care what part of the mesh the player is looking at. It may sound like Nanite is much better than traditional LODs, but each Nanite LOD has to generate in real time, which slows down processing times. Typically, I still prefer Nanite because it saves me the work of making LODs, and the processing time of Nanite is not too bad. So this begs the question of, can I use Nanite meshes with ISMs and HISMs? The answer is yes for ISMs, and why would you do that for HISMs? HISMs are already using an LOD system, so it doesn't make much sense to add another LOD system on top of that. The main draw of using an HISM is the LOD per instance, which means you're using an LOD system. ISMs could also be using an LOD system, but it's less common because at that point most people convert it to an HISM, so we're just going to assume we're only adding mesh LODs to HISMs. Since ISMs typically aren't used with LODs, using Nanite meshes can be a really effective way to simplify geometry to get back some frames per second, especially in this scene where a lot of the geometry isn't even visible. Nanite does save time on GPU performance by reducing geometry, which is why this benefits the frames per second. So to sum up everything we learned, and to determine when you should use static mesh actors / components versus ISMs or HISMs, I have a helpful flowchart. The first question is, do I need logic that will be needed per instance? Meaning, they need to be individually affected by gravity, physics, player interactions, collisions, need separate materials, etc. If so, use static mesh actors or components. If all their settings can be shared, then we need to ask how many instances would you have of this mesh. If only one, just have it be a static mesh actor. My general rule is if you have between 2 and 100 meshes that could be instanced, do it if it's easy to place them using your tool or the tool I provided. As you go up from 2 to 100 meshes, you should consider spending increasingly more time instancing, since the benefits increase with each additional instance. Once you get over 100, it's pretty much always worth your time to instance. Using the tool we provided, it should only take like 15 minutes at most. Even if you need them to be at certain points, you could always use the Place at Spline Points feature to get really specific instancing locations. But back to the flowchart. If you are using instancing, I recommend going with HISMs for UE4, even if you only have one LOD of your mesh. And for UE5, I recommend using ISMs and considering using Nanite to simplify your instances rather than using HISMs. This is a very general guide. I'm sure you can find exceptions for certain situations where you would want to use HISMs in UE5 or use ISMs in UE4, but in general, these are my recommendations. Leave a comment below if there's anything you think I missed or want to clarify anything for other viewers. I'm trying to cover a good amount of information in about 10 to 15 minutes, so there may be some information I missed. Hopefully you all now have a good understanding of what mesh instancing is and when to use it. The Spline Mesh tool now supports ISM and HISM options fully, thanks to those of you who bought the system on Fab. And even if you just download the free version, thank you for your support. If you learned something from this video and want to hear more in the future, you can subscribe to the channel. I don't post here too often, but when I do, I try to make sure it's worth your time. Thanks for watching. Until next time.